I'm Sergey Vinogradov from Intel, and today I would like to present our work that we did together with our colleagues from University of Bristol. The goal of our work was to compare two programming models. It's OpenMP and OpenCL. Why we choose these two programming models? So the reason that it's established and widely used programming model in HPC world, and with the new standard of OpenMP that allows you to offload computation to some accelerator devices, its comparison especially interesting. And initially, our work was targeted to compare this programming model on the Intel Xeon Coprocessor. And we decided to do it through an experiments, and started with working with some benchmark suite called Rodinia. And after we learned something during this work, we decided to apply this knowledge to the real application called Rotor Sim. And again, I would like to mention that our main target was the Xeon Phi. But after that, we decided to do the same comparison on the Xeon. But in this presentation, some performance data and some specific metrics are from Intel Xeon Phi. And this is what we will see during this talk. So I will go through our experiments with the Rodinia benchmark suite, show you what we learn, and after that, we will go to the application developed by the University of Bristol and see how we applied our knowledge to implement an OpenMP version of this application. And at the end, maybe we will hear our answer about which programming model is better. So this is the environment setup that we use. So what I'd like to mention is that we used NUMA systems for both for benchmarks and for the real application. It consists of two Xeon sockets with one connected mic cards. And from the software stack, we used Intel compiler. It's the latest one that we have by the moment of our work, and the latest GCC compiler. And also we use Intel OpenCL SDK that allows you to offload some work to Intel Xeon Phi. So we started with the Rodinia benchmark suite. It's a benchmark suite developed by University of Virginia. And it has equivalent implementation in three programming models. It's an OpenMP, OpenCL, and CUDA. And we were interested only about two of them. And after that, we worked with the Rotor Sim that's developed by University of Bristol. It's a multi-grid computation fluid dynamic code that simulates the work of the helicopters. So now let's start with Rodinia experiment. So for each benchmark, we chose it from the Rodinia suite. We did two experiments. First one, when all computation done on the Xeon Phi. And the second one, when your application starts on the Xeon, but computational part offloaded to the Xeon Phi. And we measured only computation time. And in case of offloading, we also measure data transfers that happens when you upload data to Coprocessor and return results back. And for our work, we chose only 5 benchmarks from this suite. The reason that we choose these 5 benchmarks is that we found an article in the internet that compared OpenMP and OpenCL programming model for the CPU. And this article mentions these 5 benchmarks and shows that there is some performance gap between OpenMP and OpenCL versions. But they did not provide the reasons for that. So and here, this is the initial results that we captured from the Xeon and Xeon Phi. So our first step was actually to port OpenMP version to offload mode. So I mean, we extended the code with target pragmas and captured initial performance data on Intel Xeon Phi. And we see that in all cases, mostly in all cases, we can some gap between these two programming models, and in all cases, OpenCL is better. And especially for LU decomposition benchmark, we have a very huge performance gap. It's more than 100x. So, and we decided to go through each of these benchmarks and to see what are the reasons for such differences. So we started with the HotSpot. And during our work, we actively used Intel VTune. And in this presentation, I will have some pictures from the VTune. So I think maybe someone already know about this tool. Yeah, if no, I have another session today during the evening, and I will talk about, especially about the VTune and its new feature to support analysis OpenMP application. And this is the initial summary view captured by VTune from Intel Xeon Phi. And the big advantages that we had when we started this work, since we were allowed to compare two implementation, and we can see the differences between OpenMP and OpenCL. And according to this view, we identified the three factors that introduce performance gap. So the first one, it's obvious, and we can see that the OpenMP version retired more instructions than the OpenCL. And the second one, it's an estimated latency impact. It's a metric that is provided by the VTune, and it approximates the number of cycles that's required to survive L1 misses. And another measure factor, it's a poor vectorization. So for Intel Xeon Phi, in case we are using a single precision, the vectorization metric should be around 16. But in that case, it's only for OpenMP, it's only about 4. It's Sorry, could you repeat? Yes, I will talk about that. So, and we started analyzing the source code. And the first difference we found between these two implementations, it's how is initial working set divided on the chunks. And in case of OpenMP, seems that parallel flow pragma was applied just to the serial version of algorithm, and it has a raw measure work distribution. While OpenCL was more mature, and it's used a blocking work distribution. And the data access stencils that is used in this benchmark, so when you need to calculate the value from each cell, you are depending on the neighborhoods from the right, left, top, and bottom. And in that case, from the point of data locality, the blocking work distribution is much more better. And in that case, you have a better cache reusage. And our solution was to implement the same blocking manually in the OpenMP code. So we just implemented our own loop across the blocks. And inside this loop, we just calculating the boundaries of each blocks and do processing of each block separately. And after that, we found that the latest Intel C++ compiler, it's 16.0. I think right now it's on the beta stage. It's provides an capability to do blocking automatically by using some special pragma. But anyway, we did it by ourselves, and actually we select the block size during an experiment and found that 16 it's optimal block size. And we think that it could be two reasons for that. The first one is that the length of the vector register on the Xeon Phi, it can process 16 images. And another my point, it's data size required for one chunks, and with such block size, it's exactly fit to L1 cache. So I mean that since each core can execute up to 4 threads, L1 cache in that case is able to capture 4 blocks simultaneously.
Did the OpenCL version compile automatically?
Yeah, so this is what we found, that when you are programming with the OpenCL, it's forced you to think in terms of vectorization and better data locality, since you are coding in terms of working items and in D ranges, and you're already thinking about how your code will be distributed across the working threads. But in case of OpenMP, sometimes developers can forget about that. And it's responsibility of the developer to keep it in mind. So once we improved the data locality, we start working with vectorization. And we found that, again, the approach with the work item and in D range is more vectorization friendly. So, and the kernel that's writing in these terms vectorized by the OpenCL compiler mostly by the default. While in the OpenMP version, we found that there is some branches in the inner loop that was targeted to process boundaries of the matrix. And our solution was to separate the boundaries processing and the internal area processing. We just created a separate loop for boundaries processing. And after that, we... no, I will talk about that. Yeah. And the last step was to apply a Pragma OpenMP sim to the innermost loop, since when we saw the compiler vectorization report, it says that there are assumed dependencies, but we was sure that there is no dependencies and this loop can be safely vectorized. So after that, we got a vectorization on the OpenMP code. So, and on the last, this is the answer to your questions about boundaries processing. So there is still one difference in implementation between OpenMP and OpenCL. It's how boundaries process it. So in OpenMP, we just move boundaries processing to the separate loop. In OpenCL, they just added a special hello element on the boundaries. So they just extended the initial matrix with additional elements and do unique processing.
OpenCL that doesn't have the bound check because they expanded your the matrix, so you don't need to go back. They guarantee you computation will be within the boundary.
Yeah.
That is different.
Yes, but our goal was to prove that with OpenMP you can reach, and we are not saying that the OpenMP or OpenCL is better right now. We just invest our time to OpenMP implementation. Once we get a better performance or better or similar performance with OpenMP, we stop our work and say, so see this, we reached it. And there are 2 points that's specific for Intel Xeon Phi. So to decrease TLB misses on Xeon Phi, we forced runtime to use big pages for arrays that's more than 64 kilobytes. And OpenCL did it by default. It's already enabled. And also we set up a affinity for OpenMP working threads, and again, OpenCL already set up such affinity by default in the configuration. So I will provide the final results after we go through all of these benchmarks. And now let's go to the second benchmark. It's a LU decomposition or LU factorization. And in that case, we saw the biggest difference between OpenCL and OpenMP. It's more than 100x. And once we started investigation, we found that there is a difference in the algorithm used in these two implementation. And our first step was to forget about optimization and just to implement the similar algorithm with OpenMP. And here is the picture which is demonstrate how it's a blocking LU factorization and how it works on each iterations. You are working with some part of a matrix. On the first iterations, you working with the whole matrix, and from iteration to iteration, you are decreasing the size. So there are three groups of blocks. So matrix divided to the blocks. It's a diagonal block, perimeter blocks, and internal blocks. And parallel part of the algorithm calculates the internal blocks. And once we implemented the same algorithm with the OpenMP, and again enabled vectorization with the Pragma OpenMP SIMD, and on the mic, we enabled again a huge pages to avoid the TLB misses. We get the same performance with the OpenMP. And here is the first interesting point we found in the LUD. So processing of each internal blocks depends on the two perimeter elements from the left side and from the top. And once you are processing once you are using the values from the P left and P top directly from the global matrix memory, it's in that case compiler produce gathers instructions on the Intel Xeon Phi because compiler doesn't know the size at the compilation time, and in that case the stride is unknown. And in that case, compiler generates gathers. But the exactly. Yeah.
Did the OpenCL also do the copying?
Yes, in OpenCL you can just use a keyword, call it local, and to copy data to the local arrays. And we did the same. We introduced two arrays on the stack, left and top, and just copying data before processing to these local arrays, and after that, the processing part is well vectorized. Another interesting point related to reduction, so it was mostly the last step in our work. So we had three loops, and on K loop we have a reduction operation on the scalar sum variable. So in case we have a block size equals to 16, the K loop completely unrolled and vectorized, and the multiplying executes in one vector instructions. But after that, we have a reduction operation that should reduce all data received after the vector multiply to one scalar variable. And it's also decrease the performance. And our solution was to switch to loops, it's K and J, and introduce not just one variable, call it sum, but introduce the array that is equal to the number of iterations on the J loop. And in that case, these multiply and reductions executed in one vector instructions. And after that, we have one more additional loop across the sum array. And this is also completely vectorized and executed through one vector instruction. So the same behavior in the OpenCL version. And the last step, that demonstrates the power of the big pages on the Intel Xeon Phi. So initially we saw some number of L1 TLB miss ratio, and we found that when we enabled big pages in compiler runtime, it's allow us to avoid TLB misses, and it impacts the total execution time. Yes, it's around. I will show the final results. So for computation fluid dynamic benchmarks, after we had experience with the two previous benchmarks, it was very easy to reach the same performance with OpenMP version. So we found that initially this benchmark has just a single loop across the particles, and for this loop there is a Pragma OpenMP parallel 4, which prevents vectorization from the compiler. And our solution was to implement our manual blocking, but it could be also done with the new Pragma. It's call it Pragma OpenMP parallel 4 SIMD that can do vectorization for you automatically. Once we rewrite this benchmark for blocking, we enabled vectorization. But we found that we still have some gap between OpenCL and OpenMP. And we found one more measure and widely experienced difference in implementation. So OpenCL uses the structure of array, while OpenMP uses the array of structure. And we know that array of structure is natural to programmer, but structures of array is more vectorization friendly and can allow you to reach a unit straight memory access. And on the fourth benchmark, it was also very easy, since we found that again OpenCL implements blocking, while OpenMP was mostly naive implementation, and we just implemented the same blocking, enabled vectorization, and set up affinity and big pages for the Intel Xeon Phi, and get the similar performance with the OpenMP. And with the last benchmark, it was very curious, since we found that implementation of this benchmark consists of two kernels, and for some reason we don't know, for OpenMP version, the second kernel was not parallelized with OpenMP. We just added Pragma OpenMP parallel 4 Pragma and got the performance. So, and here's, this is the final results that we get for each benchmarks. To be more fair, we also included GCC version of OpenMP. And we can see that for all benchmarks, we achieved the same or even better performance for OpenMP versions. And there is a huge difference in the hotspots. And this is because of, we think, because of processing boundaries, the differences in the processing boundaries. And another reason, we experienced some NUMA effects on the, our host. And we found that with OpenMP, you can fix it with just setting up one environment variable that binds OpenMP working threads to hardware threads. While our Intel OpenCL implementation does not support such affinity control by default. And we tried to do it manually through some dividing the NUMA system to sub-devices, but we have no success. It was no effects. We just decrease our performance with such changes, and we stopped with it. So what we learn from this work? So the first point that we would like to highlight is that very often when people talked about performance comparison of two programming models. In fact, they comparing not a programming model, but implementation of benchmarks. And it's mostly a competition between different programmers who optimized his implementation better. And for the fair comparison, we think that in ideal cases, maybe we can take a two team of programmer and force it to one team will optimize OpenCL version, another team will optimize OpenMP version. And the big advantage is if this team could see the results of each other and see the optimization steps applied in all implementations. And maybe in that case, we can reach the best optimized code for both versions, and in that case, we can compare two programming models. And also, we found the main factors that impact the performance. So, of course, for modern processors, and especially for Intel Xeon Phi, vectorization is very important. And with OpenCL, it's mostly provided by the default, since you're already writing your kernels that is vectorization friendly. But with OpenMP, you should keep it in mind by yourself. Another factor is data locality. So, and again, with OpenCL, this programming model forced you to think about data locality. While in OpenMP cases, we found that in most cases, Pragma OpenMP parallel 4 was applied just to the serial version. And there was not an efficient memory access pattern. And also some two factors related to Intel Xeon Phi. And for the NUMA system, it's affinity control and TLB misses on the Xeon Phi.
But you said earlier that OpenCL does affinity by its own, but not the binding. Did I get that right?
Yes. So on the Intel Xeon Phi, Intel implementation of OpenCL supports binding.
Okay.
But not on Xeon.
Yeah, but not on Xeon. I don't know the reason. So, and if you need more details about this work on the Rodinia suite, so we on the James Render's book. It's a chapter 20. And the source code is available on the website. And you can find also we contribute our changes to the Rodinia owners, and they promoted to release it in the new release. So after that, we start working on the real application, call it Rotor Sim. Again, it's a multi-grid CUD code targeted to simulate the works of helicopters. And again, we set up two experiments, one for Xeon and the second one for Intel Xeon Phi. And we compare it only and measure it only simulation time, since it is hard with the existing implementation to capture data transfer time. So initially, we chose the benchmark workloads. And our choice was impacted by the two factors. We should have enough data for parallelism, but we was limited by the memory available on the Intel Xeon Phi. And this is the compromise between these two factors that allows us to compare performance on the Intel Xeon and Intel Xeon Phi. So initially, RotorSim has only OpenCL version. And our first step was to implement OpenMP version. And we used some compilers and OpenMP pragmas to implement this one. And also we found one more useful pragma, it's a collapse, that helped us to control granularity of some loops. And after we enabled OpenMP version and received correct execution, so we can see the overview performance picture. So since RotorSim has a lot of serial blocks, we cannot expect, for example, on the Xeon, a 40x performance gain when we comparing to the serial version. But we received about 7 or 8x performance improvement. And it's also good to mention that in case of OpenCL, the kernel compilation time included to runtime. And this is the implementation specific. It can be optimized more, but we have not touched OpenCL version at all, since it's very hard. So, and here, what we can see. Again, we're comparing the two runtimes. It's GCC OpenMP and Intel OpenMP. And initially, we found that the GCC version is better. And we start analyzing this again using VTune, and we found that for Intel OpenMP version, there is a thread migration across the physical cores, and which is more important, across the NUMA nodes. And this is a performance gap caused by the NUMA effects. But once we enabled binding threads to the hardware cores, we received the better performance with the OpenMP runtime, since we pin our threads to the hardware cores and decrease the NUMA effects. And this is a comparison for Intel Xeon Phi. Again, for OpenCL version, we can see that there is some time required to build kernels for OpenCL. And how we found that the affinity is turned on the on the Intel Xeon Phi by default, we just found some environment variables, tried to set it up, but without any performance gain. And for the OpenMP cases, we had some performance gain by enabling big pages again. That's helped us to avoid TLB misses. And affinity already enabled by the default on the.
What's the little white colored bar at the top? You got blue is simulation time, red is build time, but there's one more. Yeah, that and on the other.
Oops. Seems that something.
Is this a mistake?
Yeah, I think so.
Okay.
So, and now, what are our conclusion regarding to this work on the real code? So, when you deal with the benchmarks, it's easy to you to rewrite some kernels and so on, and to get maybe the best performance. But when you deal with the real code, with the huge code base, I think it's unreal to optimize every kernel or to almost refactor all code and redesign the implementation. And in that case, we just applied our learnings that we received during the work on the benchmarks and get the reasonable performance for OpenMP versions. We are sure that we are not receiving the best performance with OpenMP, but we got the reasonably good performance on Xeon and Xeon Phi. And this is our conclusions for OpenMP implementation. So all work on porting to OpenMP was done in 5 weeks. And we found that using OpenMP, it's much more easy to debug and to debug your application on Xeon and Xeon Phi than with OpenCL. And one difference for Xeon, it's affinity control on, that's provided by the OpenMP version. and it's good. And for some implementation reasons, OpenMP versions have a smaller memory footprint, so OpenCL versions, we analyzed it a bit and found that it also have some capabilities for improvements. So, right now the conclusion. So, after this work was done, we still cannot answer and suggest you that you should use exactly this programming model or another one. So, our experiment just shows that that we invest our time to optimize OpenMP and was able to reach even better performance with OpenMP. But it doesn't mean that the OpenMP is better than the OpenCL. We think that the OpenCL versions of the benchmarks and the application have some capabilities and for further improvements. And right now, the ball on this side. So, but we can talk about advantages and disadvantages of these two models. So, according to our research, we found that OpenCL offers you out-of-the-box vectorization and memory and data locality. Since you force it by the OpenMP, by the OpenCL programming model to write kernels that is friendly for vectorization and data locality. While in OpenMP cases, developers sometimes forget about these factors and just apply Pragma to initial serial implementation. And, but if you are smart enough and you keep in mind these factors, you can achieve the same vectorization and data locality. And from our point of view, OpenMP is much more easy to debug and fix the bugs and catch the bugs in your implementation. So that's it. At the end, I would like to acknowledge some guys who helped us to optimize Rotor Sim application. It's Andrei Churbanov, who is from Intel OpenMP runtime team, and Paul Peterson and Larry Meadows, who helped us to prepare this presentation and provided feedback about these files, and many other guys who reviewed it and participated in the dry runs for this talk. So thank you. Questions?
One more question. You didn't say anything about aligning data to cache line boundaries?
Yes, we use it alignment in our work, but again, there were no such huge impact of this factor in that cases. That's what we found. We have not so in OpenCL it is by default, but in OpenMP we also use it alignment, but not such big improvement. One more questions? So I think that's it. We are done. Thank you.